The interesting thing is that the global semiconductor race has quietly changed from a battle over speed to a battle over architecture. For years, everyone argued about who could manufacture the smallest transistor. 5 nanometers, 3 nanometers, 2 nanometers. Those numbers became the headline. But engineering doesn't always reward the loudest metric. Sometimes the smarter move is to change the road instead of building a faster car. That's where photonics enters the picture. Most electronic chips communicate using electrical signals traveling through microscopic copper interconnects. It works remarkably well, but physics keeps presenting the same bill. As transistors become denser, electrical resistance increases. Heat builds up. More power is required to move data across the chip, and eventually, you spend almost as much energy moving information as computing it. Imagine a city where traffic jams become so severe that widening roads no longer solves the problem. At some point, you need a subway instead. Photonic technology attempts exactly that. Instead of moving some information through electrons, it moves it using light. Light doesn't suffer from electrical resistance in the same way. Multiple wavelengths can travel simultaneously through a single optical waveguide, meaning enormous amounts of information can move at once without creating the same thermal bottlenecks. The concept isn't new. Researchers at institutions like the Massachusetts Institute of Technology, Intel Labs, and IBM Research have spent decades working on silicon photonics. Data centers already use optical communication between servers because electricity simply isn't efficient enough over longer distances. The difficult part has always been shrinking those optical systems enough to fit inside consumer electronics. That's where many experts became skeptical. Built-in optical waveguides isn't like drawing another copper wire. Tiny imperfections measured in nanometers can scatter light. Temperature changes alter optical properties. Laser alignment becomes critical. Packaging suddenly matters as much as transistor fabrication itself. Every manufacturing defect multiplies. This wasn't merely a fabrication problem, it was an ecosystem problem. You need specialized materials, specialized testing, specialized packaging, specialized software, and perhaps most importantly, engineers who understand both semiconductor physics and optical engineering. That's an unusually rare combination, which explains why many Western assessments argued China would struggle to industrialize this technology quickly. Their reasoning wasn't irrational. Export controls limited access to advanced lithography equipment. High-end electronic design automation software faced restrictions. Certain optical components remained dominated by companies outside China. From that perspective, the conclusion seemed straightforward. Even if Chinese researchers produced laboratory demonstrations, mass production would remain years away. But reality has a habit of ignoring forecasts. Instead of waiting for perfect conditions, Chinese firms appear to have followed a different philosophy. Build around the restriction. It's something we've seen repeatedly over the past several years. Unable to obtain the latest EUV machines? Push older, deep ultraviolet tools harder than many believed possible. Restricted from buying certain AI accelerators? Develop domestic alternatives while redesigning software stacks. Limited access to foreign components. Increase vertical integration across suppliers. None of these responses were easy. None produced instant parity. But each reduced dependence a little more. Huawei became one of the clearest examples of this approach. After losing access to many American technologies beginning in 2019, the company faced challenges that would have crippled most consumer electronics firms. Smartphones, networking equipment, operating systems, AI processors, almost every major business encountered some form of disruption. Many analysts expected a gradual decline. Instead, Huawei started rebuilding almost every layer of its technology stack. Harmony OS evolved. Domestic suppliers expanded. Partnerships inside China became deeper. The company invested heavily in fundamental research instead of focusing only on next year's product cycle. That decision probably looked expensive at the time. Years later, it looks more like insurance. Here's something that doesn't receive enough attention. Research spending often appears wasteful until one breakthrough suddenly makes years of investment seem obvious. Semiconductor history is full of these moments. The transistor, the integrated circuit, CMOS architecture, extreme ultraviolet lithography. Each required years when outsiders questioned whether the effort was worth it. Photonic integration may follow the same pattern. Or it may not. That's still an open question. Because placing one photonic component inside a consumer device isn't the same as transforming the entire computing industry. The gap between demonstration and dominance can stretch for a decade. Yet there's another detail we haven't discussed, the one that may matter more than the chip itself. Who actually built the manufacturing ecosystem behind it? Because if the answer isn't Huawei alone, then this story becomes much larger than one smartphone, and much more difficult for the rest of the semiconductor industry to ignore. For years, discussions about China's semiconductor industry focused almost entirely on manufacturing nodes. Could it produce 7-nanometer chips? Would it ever reach 5 nanometers? How far behind was it compared to the world's most advanced foundries? Those questions mattered, but they also distracted people from another reality. A semiconductor ecosystem isn't judged only by the smallest transistor it can print. It's judged by whether thousands of companies can solve thousands of engineering problems at the same time. That's much harder. Think about what happens when you buy a smartphone. Most people see one brand on the box. Inside that device, though, hundreds of suppliers have contributed something. Memory chips, sensors, radio frequency modules, power management circuits, packaging materials, display drivers, precision chemicals, testing equipment, optical components. One missing piece can delay an entire product launch. This is why governments care so much about semiconductor supply chains. The factory is only the visible tip of the iceberg. The real advantage comes from the network underneath. And that's where China's strategy becomes easier to understand. Instead of depending on one national champion, policymakers gradually encouraged entire industrial clusters. Shanghai focused heavily on advanced manufacturing. Shenzhen became an innovation hub, linking design companies with hardware manufacturers. Wuhan invested in optoelectronics. Suzhou expanded packaging and testing capabilities. Universities trained engineers, while provincial governments supported suppliers that most consumers have never heard of. It's not glamorous. No one makes YouTube thumbnails about specialty photoresists or wafer polishing chemicals. But without those companies, nothing else exists. Huawei benefited from that expanding ecosystem more than almost anyone. People often imagine Huawei building everything itself. That's not really how modern technology works. The company designs key technologies, coordinates suppliers, invests in research, and integrates finished systems. Around it sits an enormous network of domestic firms solving highly specialized problems. One company improves optical packaging. Another develops silicon waveguides. Another refines advanced substrates. Another focuses on precision testing. Individually, none looks revolutionary. Collectively, they begin changing what's possible. Remember the skepticism from earlier? The assumption was that export controls would isolate individual Chinese companies. What seems to have happened instead is that those restrictions encouraged deeper cooperation inside China's domestic industry. That doesn't mean sanctions failed completely. They clearly slowed access to leading-edge equipment and forced companies into expensive workarounds. American officials would rightly argue that China's progress would likely have been faster without those restrictions. That's a fair point. But slowing someone down and stopping them are two very different outcomes. History reminds us of this repeatedly. During the 1980s, Japan appeared unstoppable in semiconductors until competition shifted. South Korea later emerged by investing heavily in memory manufacturing. Taiwan built an entirely different model centered around dedicated foundries. Each success came from identifying a structural advantage rather than copying everyone else. China seems to be attempting something similar. Rather than winning every technological race simultaneously, It's looking for areas where architecture itself can change. Photonic integration could be one of those areas. Notice the wording carefully. Could be. There are still significant technical barriers. Photonics works exceptionally well for moving data, but electronic transistors remain superior for many forms of logic computation. Integrating both systems efficiently requires complicated hybrid architectures. Manufacturing yields remain challenging. Thermal stability still matters. Cost remains higher than conventional approaches in many applications. Those aren't minor issues. They're exactly why companies around the world continue researching rather than declaring victory. Here's where the story takes an interesting turn. Many observers assumed Huawei's consumer device announcement was mainly about marketing. Show an experimental feature, generate headlines, demonstrate resilience. But what if that's not the primary objective? Consumer products perform another function. They validate manufacturing. A laboratory prototype proves physics. A shipping smartphone proves production. Those are completely different achievements. If millions of devices leave factories with consistent quality, engineers gain something even more valuable than publicity. They gain manufacturing data. Every returned unit, every reliability report, every environmental stress test improves the next generation. In other words, customers unintentionally become part of the learning process. That feedback loop is incredibly difficult for competitors to ignore because it accelerates improvement with every production cycle. This brings us back to something mentioned near the beginning of the video. The real competition may no longer be about who invents photonic chips first. It may be about who learns to manufacture them efficiently first. Those sound similar. They're not. One wins academic conferences. The other reshapes industries. My own view is that people on both sides of this debate sometimes overstate their case. Some commentators immediately declare China has already surpassed everyone. Others insist nothing meaningful has changed because the technology isn't perfect yet. Reality usually sits somewhere in the middle. Huawei doesn't need photonic chips to replace every electronic processor tomorrow for this development to matter. It only needs to prove that integrating advanced photonic technology into consumer electronics is commercially possible. Once that threshold is crossed, the conversation changes completely. Because the next question isn't whether it can be done. It's how quickly everyone else has to respond. There's one final point that I think often gets lost whenever conversations about technology become geopolitical. We tend to imagine innovation as a finish line. One country wins, another loses, and the race is over. Technology has never worked that way. Every major breakthrough simply changes where the next competition begins. If Huawei has genuinely succeeded in placing meaningful photonic integration inside a consumer device, the headline isn't that America was defeated or that China suddenly dominates the semiconductor industry. The headline is that the frontier has moved. And frontiers have a habit of forcing everyone to move with them. Remember the assumption from the opening? The belief wasn't just that photonic chips were difficult. Almost everyone agreed they were difficult. The real assumption was that China's manufacturing ecosystem wasn't mature enough to commercialize them at scale. That's a much bigger claim, because once a company ships millions of products instead of publishing laboratory papers, you're no longer debating theory. You're evaluating manufacturing. That distinction matters. History shows that laboratories invent technologies. Factories decide who profits from them. Look back over the last 50 years. The transistor wasn't valuable because it worked once inside a research lab. It became valuable because companies learned how to manufacture billions of them reliably. The same happened with LCD displays, lithium-ion batteries, solar panels, and smartphone cameras. Production is where technological leadership becomes economic leadership. This is why governments across the world aren't only investing in research anymore. The United States passed the CHIPS and Science Act to strengthen domestic semiconductor manufacturing. Europe launched its own European Chips Act. Japan is supporting advanced semiconductor production through partnerships and public funding. South Korea continues investing aggressively through companies like Samsung and SK Hynix. Nobody is spending tens of billions of dollars simply because chips are interesting. They're doing it because semiconductors increasingly determine economic competitiveness, artificial intelligence, military capability, healthcare equipment, telecommunications, autonomous vehicles, and almost every advanced industry you can think of. A tiny piece of silicon now influences global politics more than many natural resources. That's remarkable when you stop and think about it. But there's another lesson hidden inside this story. Restrictions can delay technological progress. They can increase costs. They can force companies into uncomfortable engineering compromises. What they rarely do is eliminate the incentive to innovate. Sometimes they actually increase it. That doesn't mean sanctions are ineffective. They clearly influence timelines, supply chains, and investment decisions. Yet engineering has a stubborn habit of finding alternate routes when one road closes. It's almost like water. Lock one channel, and eventually it starts flowing somewhere else. Whether Huawei's photonic approach becomes the industry standard is still uncertain. Engineers outside China are pursuing different solutions at companies, universities, and research institutes around the world. Some believe advanced electronic packaging will remain the better answer. Others argue optical interconnects will dominate only AI servers before reaching smartphones. A few think hybrid systems combining both technologies will ultimately win. Personally, I think the hybrid path looks the most convincing. Electrons are exceptionally good at computation. Photons are exceptionally good at communication. Asking one to replace the other entirely may be the wrong objective. Asking them to work together feels much closer to where semiconductor engineering has been heading for years. Of course, predictions are dangerous in this industry. 20 years ago, very few analysts expected smartphones to become portable AI platforms. 15 years ago, hardly anyone imagined sanctions would accelerate domestic semiconductor ecosystems as much as they have. 5 years ago, many people believed advanced AI chips would remain a niche product for researchers. Technology enjoys embarrassing forecasters. So here's the question I keep coming back to. If a company can commercialize a technology that much of the industry considered too difficult for its manufacturing ecosystem, what other assumptions are we still treating as facts? That question may prove far more important than one smartphone. Because today's consumer device often becomes tomorrow's industrial standard, and today's impossible engineering problem sometimes becomes next decade's ordinary product. We'll only know which path photonic chips follow after several more years of manufacturing, competition, and real-world performance. But one thing already seems clear. The semiconductor race is no longer being fought on a single track. It's spreading across manufacturing, architecture, materials science, software, packaging, and supply chains, all at the same time. That makes predicting a single winner almost impossible. My prediction is this. Over the next 5 to 10 years, we won't see one country completely dominate advanced semiconductors. Instead, we'll see multiple technology ecosystems emerge, each optimized around different strengths. Some will lead in fabrication, others in AI accelerators, others in memory, and others in photonic integration. The era of one unquestioned center of semiconductor innovation is gradually giving way to a far more competitive and far more fascinating global landscape. And honestly, that's probably healthier for innovation than most people realize. If you enjoyed this deep dive, let me know what topic you'd like to explore next. The most interesting technology stories are usually the ones hiding behind a single headline. The most interesting part of this entire story isn't that Huawei may have placed a photonic chip inside a consumer device. It's what that says about the direction of the semiconductor industry as a whole. For decades, technological leadership followed a relatively predictable pattern. A breakthrough happened in a research lab, a handful of companies commercialized it, and everyone else spent years trying to catch up. The leaders enjoyed a comfortable advantage because the barriers to entry were enormous. That model is beginning to change. Today's semiconductor race isn't defined by a single breakthrough. It's being fought across dozens of different fronts at the same time. Chip architecture, packaging, advanced materials, software optimization, AI accelerators, memory technology, power efficiency, and increasingly, photonic integration. Winning one battle doesn't guarantee victory in the war. That's why I think some of the headlines surrounding Huawei miss the bigger picture. Supporters immediately declared this as proof that China had overtaken the West. Critics dismissed it as little more than clever marketing. Both reactions oversimplify a much more complicated reality. The real significance isn't whether this particular photonic implementation is perfect. It's whether it signals that China's semiconductor ecosystem has reached a point where advanced ideas can move from research papers into products people actually buy. Those are two completely different milestones. A laboratory prototype proves that engineers solved a scientific problem. A commercial device proves that manufacturers solved thousands of engineering problems simultaneously. Think about everything that has to go right before a phone reaches your pocket. Materials must meet quality standards. Components have to survive extreme temperatures, drops, humidity, and years of daily use. Production yields must be high enough to keep prices competitive. Software has to recognize and support the new hardware. Suppliers must deliver millions of identical parts on schedule. One breakthrough doesn't solve those challenges. An ecosystem does. That's the lesson I take away from Huawei's progress. Whether the company becomes the long-term leader in photonic technology is still uncertain. Competition isn't standing still. American companies continue investing heavily in silicon photonics for AI data centers. European research institutes are exploring new optical architectures. Japanese manufacturers remain leaders in advanced materials. South Korea continues pushing packaging and memory innovations. Nobody is waiting for anyone else, and that's exactly why this race has become so fascinating. Every major player is solving a different piece of the puzzle. Eventually, those pieces begin to connect. Personally, I don't believe photonic chips will suddenly replace conventional processors in every smartphone next year. Electronic transistors remain incredibly efficient for logic operations, and decades of optimization can't be replaced overnight. What I do believe is that hybrid computing is becoming increasingly inevitable. Use electrons where they make sense. Use photons where they offer clear advantages. Let each technology do what it does best, instead of forcing one to replace the other. That's usually how engineering evolves, not through complete replacement, but through integration. There's another reason this matters beyond smartphones. Artificial intelligence is placing unprecedented pressure on computing infrastructure. Every new AI model demands more bandwidth, more memory movement, and lower energy consumption. Engineers are discovering that moving data has become almost as challenging as processing it. If photonic technologies can reduce that bottleneck, their biggest impact may not appear in phones first. It may appear inside AI servers, cloud data centers, autonomous vehicles, advanced medical equipment, and next-generation communication networks. Consumer devices could simply be the first visible step. That possibility is what makes this story worth watching. Not because one company shipped one product, but because it hints at where the next decade of computing could be heading. Of course, predictions in the semiconductor industry have a terrible habit of aging badly. 20 years ago, few people predicted smartphones would become portable AI computers. 10 years ago, most analysts underestimated how quickly AI hardware demand would explode. Even 5 years ago, many believed China's semiconductor ambitions would remain heavily constrained for much longer. Reality tends to surprise everyone. So here's the question I'd leave you with. If one assumption about China's manufacturing capabilities has already been challenged, how many others are we still treating as unquestionable facts? I'm not claiming Huawei has already won this race. I don't think anyone has. But I do think the race itself has become far more competitive than many expected, and that's good for innovation. Competition forces better ideas, faster engineering, and ultimately better technology for everyone. My prediction is that over the next 5 to 10 years, the semiconductor world won't revolve around a single dominant technology or a single dominant country. Instead, we'll see specialized ecosystems emerge, each leading in different areas, from AI accelerators and advanced packaging to memory, fabrication, and photonic computing. And if that happens, historians may look back at the first consumer device carrying a meaningful photonic chip as one of those quiet moments that didn't seem historic at the time, but ended up marking the beginning of an entirely new chapter in computing. If you enjoyed this analysis, don't forget to subscribe and share your thoughts below. I'd genuinely like to hear whether you think photonic computing is the future or just another ambitious experiment that still has a long road ahead.